So dependability means is that can you depend on something in the future? So reliability, robustness, resilience, safety, sustainability, and so on. These are all time-oriented qualities. So with time, the qualities of the system are changing. So like yesterday, we gave an example about reliability, like we tested 251 items, and then we are able to make a frequency diagram. So then you can fit in a mathematical model to that histogram, and then we can use it to make predictions or decisions for the future. What we do is we have some belief system, then based on our belief system, we do experiments. So that's what science is all about, doing experiments and testing the hypothesis. And you're only excited when you reject the hypothesis. That makes sense?
Yeah.
If all we did this week, like when you came here on Monday, and your beliefs don't change after 5 days, that means I didn't make any impact on you. So we have to be able to change. And like we say, change is constant. You have to learn how to adapt, how to learn, how to adapt. You could use the word evolve over time as operating conditions are changing. So change will always be there in this world. And then as a human being, we have to figure out how to adapt with the change. So if you look in nature, any species that doesn't know how to adapt, they disappear after hundreds or thousands or millions of years. So you have to learn how to adapt over time. So lecture number 5 is a little more mathematical, but hopefully gives you some idea that once you look at the world, then what does it mean? And then how you can develop whole mathematical theory, then statistics is a way to estimate the parameters that you have in the mathematical model. Through experimentation, we are able to estimate the parameters. So in this module, then we'll talk about some basic reliability engineering calculations. And then, and one of the ideas that we look at is the life distribution. So why we are looking at life distribution? Because reliability changes with the time. So like if I have this pointer, I don't know when it will fail. So we say in probability modeling that time to failure is a random variable. The word random means is that you cannot predict the outcome of the experiment until you do the experiment, right? You have no way to know what will happen. If you know what is going to happen, then is there any reason to do the experiment? No, because you already know. So you are wasting your energy to do something. You already know what is going to happen. So experimentation in science always means is that you are going to expect some surprises. You're going to expect surprises. And then our hope is if I'm rational. So the key assumption is that you are a rational person. What does rational mean? Huh? I'm sorry, sir. I couldn't hear. Logical. So logical, what does logical mean? Is that, like in your life, in any science, in mathematics, we have like his idea is that we have set of axioms. We have certain assumptions. We wrote certain things. And then you're consistent with your assumptions. It doesn't mean our assumptions are correct, but at least we are consistent with our assumptions. So rational means is that if we say this is based on these assumptions, this is the best thing to do, or this is the, like his example is logical thing to do, based on applying rule 1, rule 2, rule 3, rule 4, then we do not violate from that. If I start doing different things than what are based on logic, then we don't know what will happen, because then every person is doing something different. Then science cannot work. So the idea of science means is whether I do experiment and develop logically the conclusions, whether I do them in America or Russia or Japan or China or India, my answer will be same. It cannot be different. Mathematics in India cannot be different than mathematics in China or Russia or United States. So that's the idea, that you are rational. And then we learned is that with time, so time means life of the item. So like yesterday we learned, if I said, what is the life of this pointer? You can't answer that, because this pointer could fail after 1 minute or may work for 100 hours, who knows? So then we can develop different indicators of the life of the pointer. So what was one indicator that we learned yesterday? How did you communicate life of this pointer? Which metric we use? Median is one, very good. And then what most common is the average, which is in probability, we call it the expected value. Expected value. So it's what you expect. In statistics, when we estimate it, we call it card mean that some people gamble. Teen patti, what is teen patti? So then, like a card, you have perfect knowledge about the card, right? I'm sorry? Oh, okay. Okay. But you don't know about playing cards, yeah. But you have perfect knowledge about the cards, right? You know there are 52 cards, and there are 2 colors, and then how many aces are there, and kings. And then you take 5 cards at random or 3 cards at random. Now you don't know what 3 cards will be. So then, based on the perfect knowledge, I can develop the probability that if I pick 3 cards at random, all 3 cards will be aces. So mathematically, we can calculate that. But in statistics, you don't know what is in the universe. And you pick 3 cards, and supposing all 3 cards are red, now you have to guess what is in the deck. So that is the difference between probability and statistics. In probability, you have perfect knowledge. In statistics, you are trying to infer based on the sample what is in the population. So like in India, somebody says, what is the average height of a, say, female, adult female in India? But there may be, a 500 million adult females, and you cannot measure everyone. So we may take a small sample of 100 or 200, and with very high accuracy, then we can define what accuracy that is, how much error is there. We can estimate what is the height of the female, because we need that number to design seats and to design buses and to design trains and so on. So when we design it, so we can estimate it. When we estimate it, we don't have perfect knowledge about the whole universe. So we can then, when we make probability models, if there are 2 kinds of random variables. One is discrete and one is continuous. Then you can always talk about something that is both discrete and continuous. Some parts it is continuous, some part it is discrete. So they are like two models in your course material about discrete distribution. One is binomial and other is what we call as Poisson. And then there are 5 continuous distributions which are very common in reliability, safety analysis. So the names are like exponential distribution, like normal we taught, like when we talked about Six Sigma, right? We talked about the normal. Normal is a popular name, but it is not the good name. The person that developed this distribution was a mathematician. His name was Gauss, Gauss. So Gauss, yeah. So we call typically in scientific literature, we call it as the Gaussian distribution, not normal distribution. Because the word normal is bad, as if this shape is normal and everything else is, what's the opposite of normal? Abnormal. So there's nothing abnormal about exponential distribution or Weibull distribution. So it is just in real life, people abuse a normal distribution because it has been popularized quite a bit. So everybody goes ahead and blindly uses the normal distribution. So we'll talk about like in normal, then you could take log normal, Weibull, gamma. How many of these words some of you have heard before? You have heard before? So you learned about these them? Where? Which course? Mathematics, very good. Gamma function is there in math, right? Yeah. So then we call it, when we develop the mathematical equation, then there's a gamma function, like you have gamma function, beta function, and so on. So then people base, because you're using gamma function, so we call it gamma distribution. I think purpose of our presentation is not to teach you mathematics. You know that will take 2 months or 3 months course to derive everything mathematically. But hopefully try to teach you why we do things, because that is more important than what we do, right? Many times I can teach you what to do, but a lot more important is why you are doing it. So that's the motivation for doing this. So at least we can then talk very philosophically what we are doing, why we are doing it, and then what are the benefits. Then also we can talk about what are the limitations of what we are doing. So how good what we are teaching you it is. So binomial distribution means that it's like you take a card from the deck. So you say either it is red or it is black, right? So if I take 5 cards and somebody says, what is the probability all 5 cards are red? Then I can calculate that number using this equation. So in this equation, because probability of 1 card being red, and if the deck is fair, it is 0.5. So then P is 0.5, Q is 0.5, and then we can plug numbers in this equation, and then we can calculate the probability that if I take 5 cards, all 5 cards will be red. Make sense? And what is this symbol? What is that symbol? Anybody knows? No?
M means total number of cards and K means number of red cards.
Yeah, so this symbol stands for, let us see if we can put a light here briefly. Can you put this one light on? Yeah. I can write it here for you. Yeah. Just light, so that, yeah. You can tell me where it is, then I can do it next time. Yeah. That's very good. Last one. Thank you. So this symbol is like M, K. So I think many calculators have this symbol. So that is called the combinations, right? So it says, what are the combinations of picking k objects out of m object? And what is that equal to? Anybody remembers? What's the equation for combinations? So that is m factorial, k factorial, and then m minus k factorial, right? And what is m factorial? So that mathematical is equal to m times m minus 1, and then 2 and 1. So then I can plug for given value of m and k, I can then very easily solve it. Then I can find out what is the mean value, expected value, and what is the variance. Anybody has a calculator here? Some of you on your iPhone? Or anybody has a phone? You have a calculator? Yeah, very good. So we just want to maybe teach you a couple of things. So factorials tend to be very large quantity. So if, like for example, on your phone, somebody says, what is 70 factorial? See what number you get. What is 70 factorial? See if you can calculate it. What is 70 factorial? Huh? Infinite. 1.19. Thank you. So it is approximately 1.19 times 100. Very good, very good. He's a very smart a person. So you can see this number. I'm sorry. It's okay. Huh? Yeah. So this is a very, very large number, right? This is, so it is so large. You know, in mathematics, what is the name of this number? No, but what is the name for this number? In mathematics, like if I go to your mathematics department and I say, just like we have 10 to the power 3 is 1000, 10 to the power, say, 5 is lakh, 10 to the power 6 is million. So what is the name for this number? 100. So this, let us go back to, yeah. So this number in mathematics is called Google. So what happened is the company Google, it is based on this number. So they said we deal with data, and we deal with so much data that which is almost like infinity. So that's why they called them. So what only mistake happened is when they filed their application, they misspelled Google. So in math books, we do G-A-L, but they kind of misspelled it, and they said G-O-O-G-L-E. Because Google is a very, 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 very large number. So if you go to old physics books and you say in our universe, if you pretend the universe started 16 billion years ago, and now let us pretend even you have been traveling at the speed of light for 16 billion years, and then you fill it up with atoms or elementary particles, you cannot count them up to 10 to the power 100. It's a very, 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 very large number. So this is the basis, like we are teaching in this course, is that we focus on biology. So like for example, like biomarker, right? All the new computing identity is based on retina or your thumb, right? So you could say we have 7 billion people. What's the probability 2 people will be alike? And mathematically, that probability is 0. And why is that? So we could do an experiment. So supposing we are looking at a sexual reproduction. So let us pretend is that we only have 70 males, and then we only have 70 females. So we have male 1 and male 2 and male 70. So then female 1 and female 2 and then female is 70. Not like in India, we may have adult 500,000 males, 500 million males, and 500 million. So if you do 500 million factorial, it will be very, very large number. It will have no meaning. So even with 70, then we say if you match them. So for example, this female mates with this person, you'll have one kind of a child, right? If this female mates with this person, offspring will be different, right? So depending upon who. So if you mate, so then means this female has how many choices? First one has 70 choices, right? Then second one has 69, then third one has 68, then fourth one has 67. So then we could say total number of choices, the total number of children. So you say that potentially there are like 70 times 69 and so on times 2 times 1. So that is 70 factorial. And then 70 factorial is a Google, more than a Google. So I say that even with 70 people, I have 1 Google possibilities of people. And then if you do it for million, the number will be enormous. Even if you have a Google number, what's the probability 2 people will be alike? It says that is very close to 0. So that's why in computer science, like remember yesterday we were teaching that 21st century is the century of biology. Only those people will make progress who understand biology. Physics is too old now. Not that physics isn't needed. We of course need physics in biology. So like we talk about biophysics and biochemistry. So lot of growth, lot of innovation, lot of new research, whether it is in computer science or in medicine, is based on biology. So that's the basis. When we take a marker of a person, we are very confident that this is a unique marker, that the likelihood another person will be like that is close to 0. Is close to 0. Make sense? Any questions on this idea, on basic probability? So then we can make we could calculate the mean. What is this symbol? Sigma is what? Standard deviation. So sigma square is the variance, right? And variance is the second moment. Just like a mean is the first moment, then variance is the second moment. Then you can calculate the third moment. So there is a lecture we gave yesterday. We didn't cover all the mathematical equations. So in that lecture, lecture number 3, we have all the equations. How did you calculate the moments? How you calculate the moment? So you calculate the third moment and the fourth moment and the fifth moment. Any probability model has infinite number of moments. Infinite, because you can raise it to the any integer, integer 1, 2, 3, 4, 5, 6. So you have infinite movement. So variance gives us some idea of variability. That's why we call it variance. How much variability is here? So if I have a distribution, so one distribution, let us say, is like this, another distribution is like this. So this one will have less variance than this distribution. And then in reliability, safety, quality, variance is very important. Lot of quality problems are because there is a large variance. Because we don't have the ability to consistently do things. When we make products, we cannot make them all identical. So there is a variability. If there is a variability, that means there are weak items and then there are strong items. So remember yesterday we talked about, that's why we have infant mortality. Because if you have weak items, then they'll fail very fast. And then what is left is, so like if I have a distribution here, and then if I apply certain stresses, then these items less than this, they will fail right away. So if they fail, then what is left is better, right? The average of what is left is more than the average of having the whole population. Then another distribution that we can look at is the Poisson distribution. It has only one parameter, and then we can find the mean, and we can also find the variance. And this unknown here, P, M, this is like a binomial approximation, but the main parameter is mu. Then we can estimate the mu using statistics, right? So that is the difference between probability and statistics. We can go back to here. So somebody says, how did you estimate this P? So from your populations, you can take a sample. So if I take a sample of 10 items, and I find 9 are good and 1 is bad, then I say, point estimator of good items is 9 over 10, that is 0.5. So then I could use that 0.5 number in this model. Make sense? Then another distribution that is very common is called Weibull distribution. Weibull is based on work of Dr. Weibull. He was a mechanical engineer, and he will do a lot of testing of materials. And anytime he'll test a material, he will get very different tensile strength, percentage elongation. So what the different parameters of the material are. And then you can make a histogram. So every time you make a histogram, then the shape of the histogram is different. Maybe once it was like that, but then next time maybe like that, then next time maybe like that. So the shape is different. So then you say, like Gaussian distribution is just Bell, right? So you cannot change the shape, it is fixed. But many times when you do work in engineering and then you do applications, then the distribution keeps on changing. So then it would be nice if I have one distribution that can change the shape of the model. So most of this work was done in the United States by a professor called Gumbel, who worked at Columbia University in 1940s. And then what he did is he took his equations, so he worked on what we call as extreme value theories. So what is important in reliability and safety are the extreme events. Like when will bad things will happen, they are based on something extreme happening. Suddenly in India, huge flooding, that means one of these days there will be a lot of rain. And then bad things will happen. There could be a huge earthquake or big tornado and so on. So this is like extreme events. Under normal conditions, bad things don't happen. but one of these days, really extreme events will happen. So that was the basic idea. So he then published a paper in 1951 about a distribution that has a wide applicability. And then this is the mathematical equation. We don't have to go through the equations and then derive them. So for this probability model, this has like 3 unknowns. And then one can calculate the reliability. Reliability, remember, is the area in the tail of the distribution, right? So if the model is like that, if this is the time to failure, then up to here, this area is the failure time probability, then this area is the success probability. Failure probability plus success probability is always equal to 1, because total area under the function is equal to 1. So then for the Weibel distribution, we could say what is the mean, and what is the median, and what is the mode, and what is the standard deviation. So then all of those things we can easily calculate them. So you can see here there is a gamma function, right? Also, so gamma function and beta function, they are very naturally occurring things in mathematics, like exponent E, right? Under, it is so many mathematical applications in mathematics. Did you watch a movie? There was a Hollywood movie called A Man Who Knew Infinity. Yeah, you saw that? So Ramanujan, yeah. So if like I add number, and I could say, I can add 1 plus 2. Or like partitioning idea is very important in computer science. So a lot of work he did. So there is a number 4, like that, partitioning. So you say, how can you get number 4? I could get 1 plus 3, or 1 plus 1 plus 1 plus 1, 2 plus 2, and so on. So it says there is a number 100, and how many ways can you get number 100? That number is very, 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 very large. If there's a number billion, so that means numbers, total partitions will be more than Google. So the idea saying that this man knew infinity, he's able to develop a mathematical equation that no matter what numbers you have, I can approximately find how many possibilities are there. How many possibilities are there. So you could say, how could a man do that? And people even today still wonder how he did that. Nobody knows how he came up with the equation, right? So that was the challenge. People did not believe his things because they couldn't prove how he developed the equations. And then a lot of that basic work is very important today. So like when we, in cosmology, when we talk about Big Bang and matter and antimatter, so a lot of these mathematical things become important to understand the universe. So you could say there is a person almost 100 years ago. Why was he doing what he was doing? He was not worried about job or worried about employment. And then some of the work he did without worrying about job is impacting society for hundreds of years, or will impact society for thousands of years. So that essentially is the purpose of education. Not to get a job, but to do something that will help humanity, that will help any part of humanity, maybe your own society, over long term. Short term, of course, we all need jobs and food and house, right? But if we are stuck with the short term thinking, then like we have been teaching is, then you cannot come out of it, right? Then you will be there forever on survival at a very lowest level. So the idea is take the time. So that is one thing that maybe not everybody may benefit from it, So this week is a luxury for you. Yes, no? Because you can sit here and you can imagine things that you don't have. Once you leave this room, then you have to focus on survival on a day-to-day basis. Make sense? So you have a couple of hours to think at a very different level. You can reflect. Maybe you don't listen to me, but you can reflect on what you're doing, why you're doing it. So it is a tremendous luxury. And typically, for many people, this opportunity, at least in India, is very hard to get. Just sit and listen and think and reflect. Nobody's asking you to do anything, right? Only thing we are asking you to be open or receptive to learning. That's the only requirement, right? So just enjoy it and then think. The only challenge will be is that some of you don't have the training to enjoy this process, right? So people who make impact on society, you'll find that we typically say, oh, I want a job. And then most of the people's job is something that is bad, right? You have to do work and manual work or whatever work. And then you quit the job and then you go home, now you're happy. So that is very bad. Your job and your happiness and your hobby should be same. Otherwise, you can never be a productive person. Make sense? You say most of us don't have that luxury. We cannot find jobs so that your job and your happiness are the same, right? But the challenge for each person, even if you're a worker, you have a pride in what you're making, even at low level, right? And this is your job, and you enjoy what you're doing. You will do it on Sunday, you'll do it in the middle of the night. So it is not like you just work from 9 to 6 or whatever period. So the idea is for each one of you to figure out what you enjoy, and then you find something that is same. You find something that is same, right? It is not a question of money or, So you can see, like, if you look even Bollywood, Amitabh Bachchan, you think he needs money to work in a movie? He has more money than probably he can spend in 10 more lives, right? So why will he still work in movies? He enjoy working, yeah. So issue is not that you got enough money and now you can sit back home and retire. So the idea is each person has to find their own model. Doesn't mean everybody can be like him, right? But you can be something very different. You could be in a village and you can still figure out that your work and your hobby are what you take pride in. They are the same thing. They are the same thing. So each person has to do their own discovery and figure out how to do that. So you can see these shapes of this distribution, they can be many. So then using statistics by experimentation, we can fit in different models. So I could say, how do you estimate whether, if like this curve is when beta is 1, this curve is when beta is 2, then this curve is when beta is 3. If beta is 10, then the curve may be like something like this. So these distributions we say are based on the third moment. These are skewed distribution. So this will say the third moment is positive. So they are called positively skewed distribution, right? And if beta is like 4 or 5, then they are negatively skewed distribution, right? So like we talked about yesterday about income in India. So for people's income, should the distribution be positively skewed or negatively skewed? Income for people, what it should be, not what it is, what it should be. I'm sorry? Why? Negatively skewed, because the basic idea is so you can see income. So like this axis is the household income. And this is 0, and then this is infinity, right? You want people to have more income rather than less income, whatever is the value of money, right? So you want more people here rather than here. So if my distribution is something like this means what? Most of the people have very little money, and then Tatas or Reliance Brothers have lot of money. I'm sorry? Few people have lot of money, and then most of the people have very little money. So what will happen in India? So if you go to America today, it will be something similar, but you could magnify it by a factor of 10 or 5. But still, most of the societies, there is what we call as the word is, there is a concentration of wealth. So in every society today, whether it's United States or India or Africa or Mexico, people are struggling how to redistribute it. And most of the systems and economic systems are such that it is in favor of rich people rather than poor people, right? So then you cannot fix this problem by tinkering and complaining. Only way you can fix it by what was the concept we're teaching in this course? By changing the system, whether it is social system, political system, economic system, and taxation system, part of economics, and so on. So typically, everywhere there was a person, more than 100 years ago, a Professor Pareto. So he was an Italian economist. So we use the concept of Pareto analysis. You have heard that, right? So in like TQM, so that means you develop priorities. So he said when he looked at income distribution, small number have so much money and everybody else has nothing. So people call it 90-10 rule. So that would mean that 10% have 10% in a quality sense of defects, or based on one kind of a problem. So it is a concentration of the quality characteristic. So this distribution is very, very positively skewed. So in India, we say, what's the difference between India and Japan and America? So we could calculate what is the skewness. We could develop a coefficient of skewness, that's like a metric. And then we could say, what is the coefficient of skewness in India? What is the coefficient of skewness in Japan? What is the coefficient of skewness in United States? And then people figure out how to change it. But the worst thing that is happening is people have been monitoring this for the last 60, 70 years. And every year it's becoming worse. It's not getting better. It's getting worse and worse and worse. So that means smaller and smaller percentage of people have more and more and more wealth. And that means there'll be a lot of poor people. So the word poor is very relative, right? Poor in Japan is very different than poor in India, or poor in USA is different than in Japan. So it's very, very relative. But the idea is the same, that there is a concentration of wealth. And then question is, how can you break that cycle? We could then calculate like hazard rate. I think a lot of that is basic mathematics. We could calculate the equations when beta is equal to 1. So when beta is equal to 1, this distribution becomes the exponential distribution. So that's very, very common distribution. So this is like the shape for the exponential distribution. And then we can develop different metrics for the exponential. You can see exponential distribution is a very, very skewed. So you can go back. So you can see in this case, mean will be bigger or median will be bigger. Mean will be bigger or median? So we talked about this is the basic statistics, and make sure that if nothing else, you understand typical words that people use, average or mean or median. So you can see this tail will push the center of gravity towards this side. And lot of things are right in the beginning. So very soon, you will get 50% of the population, and still there is a very long tail. So your average will be pulled by all the mass that you have at this point. So that's why your mean will be a lot bigger than the median. So by mean, almost 69% of the population fail. Median was only 50. So your mean is not bigger. So that's what these kind of calculations show. It says my median means that 69.3% of the population fails by the median. Good? So you can then apply these ideas everywhere. So you can do testing, like when if you go to Dell company and you want to buy laptop or you want to buy any phone, Samsung. So then we have to do calculations. If Samsung gives you warranty, then they have to know how many phones will fail and so on. So then we can do all those calculations using these kinds of distribution. This slide just tries to show limitations of statistics. So you can see statistics by definition deals with the past. Why do I say that? Because anytime you do experiment, you collect data, it's already in the past. Statistics, but you cannot use statistics to predict the future. Then in order for you to predict the statistics for the future, you'll have to make the assumption that future is same as the constant, past. So in India, we don't want our future to be same as past, right? Yes, no? Would you want future to be same as past? No. You want future much better, right? Than what the past is, right? It makes sense? So that's why you cannot collect data in India and then extrapolate it to say what will happen next 10 years or 50 years or 100 years. Because today we're going to change a lot of things. At least smart people will try to do that. Maybe you won't do that. But if you change things, then past has no relevance. Now you are a new person. And what you will do tomorrow is very different than what you did yesterday. So that's the idea. So statistics cannot help you there. But for material, it is the same. Like if you have a steel rod. Steel rod yesterday was the same as today, and maybe it is the same material tomorrow. This global universe is not changing that fast. That prop steel rod would itself learn how to become a better material. So typically what we do is we take the data, then at this moment today we make design decisions, we act on it, and then as soon as I act on something, I change something, I get a new future. I get a brand new future. And then we'll wait for tomorrow and see what happened, and then if things are not working out, then we change our model, change our assumptions. Then day after tomorrow we'll get new results. Then day after tomorrow we'll get new results. So that's the basic idea. And then I think we had a module which we never covered on robust design. So the purpose of experimentation is to change the shape of the distribution. So if I have a process and it has this distribution, and if you want high values for time to failure, you want to change it to this distribution. Make sense? And then you can only do that is that you improve the process. It says the objective is to change the process. You have to change the process so that the output distribution is improved in terms of the quality characteristic. It won't happen by itself, right? So like we learned yesterday, a naive or not so smart person is who keeps on doing the same thing again and again and expect different results. You must do something different. So I'll repeat that hundreds of times. So make sure that you learn. So every day when you go to bed, you can think and say, what did you do different today that you didn't do day before? You think you could monitor yourself and see what you changed today based on what you did day before today. Then this is the Gaussian distribution. It has two parameters, mu and sigma. So you can see its shape is pretty consistent. Then these are some of the values of mean, median, mode, because it is symmetrical. So they are all the same. And then we can find the area under the normal distribution. These are like some of the equations to calculate failure rate, hazard rate for the normal distribution. Then we could look at log normal distribution. So you see, basic idea is the same. In a statistics course, there are hundreds of models that one can learn that you can apply. So this is the log normal distribution. This is like the gamma. So we call it gamma distribution because this gamma function. So that is the gamma function. Then you can calculate the mean of the gamma distribution, and you can calculate the variance of the gamma distribution. So this is like a summary of some of the models that we presented in this lecture. Good? Any questions? Questions? No? So we can take a 5-minute break, then we can go to the next lecture. So then the idea is we'll present 2 lectures every day and 1 tutorial. Yeah, so then we can take a little bit bigger break after the second lecture, then we'll have the tutorial number 3, and then you'll have lunch. Okay? Thank you.